Spacing equals 6 inches by 3 equals 18. The spacing between A and B is 18. Figure 11 to 12. Predetermining bend marks. Rectangular obstruction. To find bend mark A for the rectangular obstruction shown in figure 11 to 13, the formula is bend mark A, distance, d, plus 1/2 the offset constant for 45 degrees. This pipe job is using 1/2 EMT, so the offset constant is 5 inches, 1/2 the offset constant would be 2.5. Substitute values and solve. Bend mark A equals 36 inches, 2 plus 2.5. Bend mark A equals 36 inches, 4.5. Bend mark A equals 31.5, as shown in figure 11 to 13. Spacing from bend mark A to bend mark B is found by using the formula. Spacing equals d plus d squared by 1.414. Spacing equals 2 plus 4 by 1.414. Spacing equals 6 inches by 1.414. Spacing equals 8.484 or equals 8.5, as shown in figure 11 to 14. Rigid metal conduit, RMC, 12. Rigid metal conduit, RMC, includes pipe made of ferrous, steel, and non-ferrous, aluminum, copper, bronze, etc., materials. Article 344 of the National Electrical Code covers the use and installation of rigid metal conduit, RMC. This article defines rigid metal conduit as a threadable raceway of circular cross-section designed for the physical protection and routing of conductors and cables and for use as an equipment grounding conductor when installed with its integral or associated couplings and/or appropriate fittings. Quote, standard rigid metal conduit sizes are 1/2, 3/4, 1, 1 1/4, 1 1/2, 2, 2 1/2, 3, 3 1/2, 4, 4 1/2, 5, and 6. These sizes are called trade sizes. Trade sizes give the dimension for the minimum inside diameter of the pipe, rather than the overall or outside dimension of the pipe. A full listing of pipe diameter inside and outside are listed at the back of the book. The metric designator for these sizes range from 16 mm to 155 mm. Rigid metal conduit is manufactured in standard lengths and is threaded on each end. The standard thread, called the National Pipe Thread, NPT, is a U.S. standard for tapered threads used on threaded pipes. The taper rate for all NPT threads is 1/16 or 3/4 inch per foot measured by the change of diameter of the pipe thread over distance. The threaded couplings that are used to connect, or join, two pieces of rigid metal conduit together have no taper, or have straight threads, NPS. By not having a taper, more threads can be engaged, making for a better electrical connection which enables the conduit to be used as an equipment grounding conductor. Color-coded end caps, or thread protectors, are used on the end of the threaded pipe to protect the threads from damage and to keep the threads clean. Pipe sizes that are in inch sizes, I, 2, 3, 4, 5, and 6 inches are protected with caps that are color-coded blue. Trade sizes 1/2, 1 1/2, 2 1/2, and 3 1/2 are protected using black caps, while sizes 3/4 and 1 1/4 have red-colored thread protectors. The standard length of rigid metal conduit is B 10 feet, which includes a required coupling on one end of the conduit. It is worth repeating that the actual length of the conduit itself will be less than 10 inches in length, and only when the length of the coupling is added will the length be 10 feet. As with EMT, the bending qualities of rigid will be affected by the ductility, uniformity and surface treatment of the conduit, and these qualities will vary with each manufacturer. The minimum bend radius for any field bend is found in Table 2, Chapter 9 of the NEC as shown in Table 12 to 1. A field bend is any bend made by an electrician as needed for installation of the conduit. The NEC copyright limits the number of bends that may be made between pole or junction boxes to not more than the equivalent of 4/4 bends, or 360 degrees of total bend. Box offsets, IFUSED, must be counted toward the 360-degree limit. Types of rigid metal conduit benders. Rigid pipe may be bent using several different types of benders: Hickey benders, mechanical benders, electrical benders, and hydraulic benders. Manually bending rigid pipe using a Hickey bender. For hand bending, a Hickey-style bender is used. Figure 12 to 2 shows a Hickey bender that is used when precision bending is not required. The Hickey is normally only used when the conduit is to be embedded in concrete or buried for underground work. Effective bending with a Hickey is limited to pipe sizes 1/2, 3/4, and 1. Conduit larger than 1 inch would require more strength than most electricians possess. As with hand EMT benders, constant pressure must be applied with the foot to prevent irregular bends. As there is no footpiece on a hickey, the pressure must be applied to the pipe, just behind the bender, as shown in figure 12:3 and 12:4. Accurate bending with a hickey is difficult without many hours of experience, but acceptable bends can be made by the beginner. The correct method for bending a 90° stub with a hickey is to make several smaller degree bends. Place the hickey bender on the pipe where the 90° bend is to start. Pull a small degree bend, slide the bender down on the pipe and bend again. Continue to bend small bends, called bites, while moving the bender after each bend until the full 90° bend has been achieved. After the third or fourth bend has been made, check the stub length, as shown in figure 12:5. If the stub length is going to come up short, move the bender further down the pipe than you did for the first 3 or 4 bends, take bigger bite, and bend more degrees to make the stub come out to the right height. If the stub is coming up long, reverse the hickey head on the pipe and push some of the bend out. Return the hickey head to the normal position and take shorter bites, with more bend per bite, to finish the bend. While it is possible to bend a 90° bend with one pull on the bender handle, the resultant bend would have a radius that is usually too small, too tight, and would make wire pulling difficult, if not impossible. See Table 12:1. Rough take-up values for bending 90° stubs are shown in Table 12:6. Take-up will vary with hickey type and the material that the conduit is made of. Use these take-up figures and lay out the pipe as described for 90° stubs in Chapter 3 for a starting point. Mechanical benders. Chicago-style mechanical benders like the one shown in Figure 12:7 can be used to bend rigid metal conduit, steel and aluminum, up to 2 inches trade size. This style bender can also be used for bending EMT up to 2. This style of bender can produce very accurate bends with little physical exertion on the part of the electrician. Bending techniques for Chicago-style benders are covered in Chapter 13. Electrical benders. Figure 12:8 shows one style of electrical bender that is capable of bending rigid conduit, EMT and IMC in sizes 1/2 through 2. No need to change shoes, as the shoes are all included in one casting. Though the shoe design is convenient, what makes the cyclone bender unique is the solid-state circuitry that allows you to dial in the desired angle of bend from 1 degree to 105 degrees. The cyclone even compensates for spring back and requires no physical effort to bend the conduit. Figure 12:8, Courtesy Gardner bender. Hydraulic benders. Figure 12:9 shows a Greenlee GL 880 hydraulic bender that can bend up to 2 inches rigid conduit. Figure 12:9, Greenlee GL 880 hydraulic bender. Courtesy Greenlee. Hydraulic benders are available that will bend up to 6 inches rigid metal conduit. Hydraulic bending techniques are covered in Chapter 14. Bending with a mechanical style bender 13. The mechanical ratchet style bender, as shown in Figure 13:1, is a great bender for various sizes of EMT, rigid, IMC, and aluminum conduit. This style of bender is frequently referred to as a Chicago bender. One of the first manufacturers of this style bender was the Lindsay Company from NC. They called their bender a Chicago bender, and the name became synonymous for any mechanical bender of this style. While one person can successfully bend conduit using this style of bender, it is easier if 2 electricians work together. While one is watching for alignment and leveling, the other operates the ratchet handle for bending. With careful layout and by following the proper procedures, bending conduit with this type of bender becomes an art form. While not all electricians are capable, nor aspire to this degree of proficiency, for those that do, this is the style bender that makes it possible. The ratchet mechanism that engages the notches on the bending shoe that causes the shoe to rotate is called the pawl, as shown in Figure 13:2. There will be a release mechanism on the bender frame that will disengage the pawl from the shoe, so the shoe can be rotated to remove the conduit after the bend has been made, or to move the pipe forward. The jaw, or front of the bending shoe, will be used as a reference for bending, the same as the arrow on a hand EMT bender. All benders of this type will have a degree scale, or degree indicator, that is part of the bender to indicate the degree of bend that has been made. The accuracy of these degree indicators are questionable, especially on older or well-used benders. The scale can be used effectively, however, if some scrap pieces of pipe are bent using a level and then making notations or corrective marks, in pencil, on the scale to indicate when a 45 degrees and 90 degrees bend have been achieved. The take-up as measured from the front of bending shoe can also be found while checking the accuracy of the bending indicator scale. Write the take up on the shoe in pencil. Do not rely on someone else's notations about scale accuracy or take up. You are responsible for the conduit you bend, so establish your own figures. For accuracy of bends and ease of bending, level the bender frame. If the work surface is rough and uneven, use a piece of plywood to give yourself a good solid, level work surface. By having the bender frame level, precision offsets, 90° stubs and multiple bend pipe jobs are greatly simplified and will produce results that you can take pride in. The same procedures outlined in previous chapters for bending 90° stubs, kicks, offsets, and saddles with EMT will apply to bending rigid metal conduit. The only difference will be that the front of the bending shoe will be used as a referelche, instead of using the arrow as we did on the hand bender. When bending rigid conduit, the accuracy of your bends has added importance as the conduit must be cut, reamed and threaded. Pipe that hits right the first time, without additional cutting and threading to make it fit, more than pays for the little extra time that was spent on calculating the location of the bend marks. If a magnetic angle finder is not available, an alternate method for bending angles less than 90° is the amount of travel. Amount of travel method. The basis for this method is the fact that for any given pipe size, the same amount of pipe will be drawn, travel, into the bender and formed around the radius of the bending shoe every time a bend is made. The relationship between the amount of conduit travel and the degree of bend can be used to bend various degrees of bend. Example. If 10 inches of conduit travels into the bender for a 90° bend, only 5 inches should travel into the bender for a 45° bend. To apply the method: 1. Carefully level the bender frame. 2. Insert a straight length of conduit into the bender. Attach the front jaw to the bending shoe, release the pawl, lift the handle and engage the ratchet. Lower the handle, letting the weight of the handle hold the conduit in place. 3. Using the back of the conduit support, bending shoe back plate assembly, or other convenient non-moving part as a reference, place a mark on the conduit as shown in figure 13-5. 4. Bend a full 90° bend, checking carefully with a level for accuracy and adjusting for spring back, the amount the bent pipe tends to straighten when pressure on the ratcheting mechanism is released. 5. Using the same spot on the bender as you used to put the first mark on the conduit, make a second mark as shown in figure 13-6. 6. Remove the pipe from the bender and measure the distance between your first mark and your second mark. This measurement is the amount of travel for a 90° bend for this size of conduit using this bender. To find the amount of travel for any given angle of less than 90°, divide the amount of travel by 90, and then multiply the answer by the number of degree you want to bend. Example. If the total amount of travel for 90° was 8 3/4, find the amount of travel for A. 22.5 degrees, B. 10 degrees and C. 17 degrees. A. First divide the amount of travel by 90 to get the travel per 1 degree. 8 3/4, or 8.75 divided by 90 equals 0.09722. Next multiply 22.5 degrees by 0.09722 to get the amount of travel for a 22.5 degrees bend. 22.5 by 0.09772 equals 2.18745 or equals 2 3/16. As accuracy with the measurement is essential, your measurements should be rounded to the nearest 1/16 of an inch. B. As we already know the amount of travel for 1 degree, we only need to multiply that amount by 10 to find the travel for 10 degrees. 10 times 0.09722 equals 0.9722 or equals 31 30-seconds, or for all practical purposes 1. C. To find the total travel for a 17 degrees bend. Total travel equals angle x travel per degree. Total travel equals 17 times 0.09722 equals 1.652 or equals 1 5/8. Once the travel has been determined, angle bends of less than 90 degrees are achieved by accurately marking and monitoring conduit travel into the bender. This method works even when the bender is not level or on a level surface. Problems. 1. If 90 degrees of travel is 10 5/8, what would be the travel for A. 15 degrees, B. 30 degrees rounded to the nearest. 2. If 90 degrees of travel is 8 7/8, what would be the travel for A. 60 degrees, B. 45 degrees rounded to the nearest. Finding total pipe length required. All of the pipe layout techniques described in the EMT section of this text may be used for bending rigid conduit using a Chicago-style bender. The same is also true for any other kind of bender, be it electrical or hydraulic. In most bending jobs, the conduit will have more than one bend and the pipe cannot be placed in a power threading, like the rigid model 300 shown in figure 13-7, so the final cutting and threading will need to be done by hand. Not a popular job for most electricians. The need to cut, ream and thread by hand can be eliminated if the total pipe length required for a given job can be determined first. A straight length of pipe can then be measured, cut, reamed, and threaded using the power threading machine. Power threading machines are sometimes called mules, in part due to the power that these types of machines can produce. Another situation where it is more convenient to cut, ream, and thread before bending the conduit is when the pipe pile and threading equipment are located some distance from the bender. To determine ahead of time how long a piece of pipe needs to be to go from point A to point B after a series of bends have been made, will require that we know the gain for each bend. Gain is the amount of pipe that is gained by bending on a radius, rather than at a right angle as shown in figure 13-8. In figure 13-8 the measurement for each length is 5 inches, if pipe could be bent at a right angle as shown the bend would require 10 inches of total pipe length, 5 plus 5 inches equals 10. Of course pipe cannot be bent at a right angle if we want to pull wire through the pipe after it is bent. Pipe then must be bent on a radius as shown in figure 13-9. If a measurement is taken from the back of the bend to the end of the pipe as shown in figure 13-8, the measurement shown for the sta is 5. The same measurement would be found if the pipe is measured from the back of the bend to the leg end of the pipe. By bending on a radius, less pipe is actually required to make the bend and still have a stub length of 5 inches and a leg length of 5. In figure 13-9, the total pipe required is given as 7 and 7/8. The difference between the 7 and 7/8 and the I0 that would be required if we bent our 90 degrees at a right angle is called gain. Gain is the amount of pipe that is gained by bending on a radius rather than at a right angle. In this example the gain would be 2 1/8, 10 inches 7 and 7/8 equals 2 1/8. The gain for a 90 degrees bend will vary with each size of pipe as well as with the type of bender that is being used. To find gain for a given size of pipe and a given bender, proceed as follows. 1. Select and measure a straight length of scrap pipe. For this example let's say that the scrap piece of pipe is 36 inches long. 2. Using the take-up for the pipe size and bender type, place the pipe in the bender and bend a 10 inches 90 degrees stub. Check the bend with a level to make sure that the bend is a full 90 degrees. Accuracy at this point is very important. 3. Remove the bent pipe from the bender and using a straight edge measure the stub and leg lengths as shown in figure 13-10. 4. As shown in figure 13-10 the stub length is 10, and the leg length is 28.5. Add the measurement of the stub, 10, and leg, 28.5, lengths together, 10, plus 28.5, equals 38.5, and subtract the original pipe length of 36. The difference, 38.5 36 equals 2.5 of gain. So the gain for a 90 degrees bend for this size of conduit and this bender will be 2.5. This gain will be unique for this pipe size and bender. A different pipe size will have a different gain for 90 degrees. The only way to find gain is to bend scrap pipe as outlined. The author knows of no way to find gain mathematically that will be as accurate as the gain found by bending a piece of scrap pipe. Consider 2 examples of typical bending jobs to find the total pipe length that would be required. Example 1. The pipe used will be 1/2, rigid with a gam of 2.5 with the dimensions as shown in figure 13-11. Note: all dimensions are measured to the back of the pipe to the end of the pipe, or from the back of the pipe to the back of the pipe, which is outside to outside. Add all dimensions. 12 inches plus 42, plus 18, equals 72 inches total of dimensions. There are 2 90 degrees bends so there will be 2 gains to consider. Gain is given at 2.5, for each 90 degrees bend. Total gain equals 2.5, x 2 total gain equals 5. Subtract the total gain, 5, from the total dimension, 72 inches, for a total pipe length requirement of 67. A straight piece of 1/2, rigid conduit could now be cut to 67 inches, reamed and threaded knowing that the pipe is the right length for the required conduit job. The bending marks can now be placed on the conduit and the bends can be made. Note: for simplicity, all examples and problems from this point on will be drawn in one-line form, box offsets and thread lengths will not be included. All measurements are to the back of the bend, or outside edge of the pipe. Example 2. This pipe job calls for 3/4, rigid conduit that has a gain of 3 3/4 and measurements as shown in figure 13-12. Add all dimensions. 16 inches plus 36 inches plus 21, plus 11, equals 84, total dimensions there are 390 degree bends, so there will be 3 gains. Gain is 3 3/4, x3 equals 11 1/4, total gain. Subtract total gain, 11 1/4, from the total dimension, 84, to get an actual pipe length requirement of 72 3/4. Now let's add an offset to our bending job and find the total length that will be required. For 90 degrees bends we subtract gain, for offsets we must add shrink. Shrink was covered in Chapter 7.0, this book. Example 3. This conduit bending job shown in Figure 13-13 will use 1/2 rigid conduit with a gain of 2.5 and 45 degrees offsets with shrink of per inch of rise. Add the dimensions. 65 inches plus 30 equals 95, total dimension. Find total shrink. The offset is 8 inches, so the shrink will be, for each inch of rise, 8 by 3/8 equals 24/8 or 3 inches total shrink. Add total shrink to the total dimensions. 3 inches plus 95 inches equals 98, adjusted total dimension. Find total gain. There is only one 90 degrees bend, so the gain would be 2.5. Subtract the gain from the adjusted total dimension. 98 inches 2.5 equals 95.5, total pipe length required. Note: remember that if you are not using Myers hubs, you must also add an amount for the threads to enter the boxes. For a double lock nut and bushing it is normal to add 3/4 to each end of the pipe for threads. Example 4. Figure 13-14 is a job using 3/4 rigid pipe. The offset will be made using 30 degrees bends. The gain for the 3/4 pipe will be 3 3/4. Shrink for the 30 degrees offset will be 1/4 per inch of rise. Figure 13-14. Add all dimensions. 13 inches plus 41 plus 28 equals 82, total dimension. Find total shrink. 30 degrees 10, offset equals 10 inches by 1/4, equals 2.5, total shrink. Add total shrink to total dimension. 2.5 plus 82 equals 84 1/2, adjusted total dimension. Find total gain. 2 90 degrees bends equals 2 by 3/4, equals 7 1/2, total gain. Subtract total gain from the adjusted total dimension. 84.5, 7.5, equals 77. 77 inches of pipe, plus threads, will be needed for this bending project. Problems. 1. Gain 2.5, shrink per inch of rise. Total pipe length _ 2. Gain 3 3/4, shrink 1/4 per inch of rise. Total pipe length _ 3. Gain 5 3/8, shrink 1/2 per inch of rise. Total pipe length _ 4. Gain 4 1/4, shrink per inch of rise. Total pipe length _ push-through bending. The Chicago type bender allows us to advance the art of pipe bending. All bends in a given piece of conduit can be made in succession without removing the pipe from the bender. After a bend is made, the pawl is released, the jaw is removed and the pipe is advanced forward to the next bend mark. The jaw is replaced, the pawl is engaged, and the next bend is made. This technique is called push-through bending. To use this technique, all bend marks for a given length of pipe are placed on the conduit first. This requires additional calculations, but will actually save time once you become familiar with the procedures used. An added benefit is the feeling of accomplishment and pride you will feel when the pipe fits right the first time every time. Let's review two terms from previous discussions: take, up and gain. Take, up is the distance from the back of the bend to the bending mark and is used to position the bender for accurate 90 degrees bends as shown in Figure 13-15. Gain is the amount of conduit saved by bending on a radius rather than at right angles as shown in Figure 13-16. Figure 13-16. Now let's assume we are bending 1/2 rigid pipe. The take-up of the bender is 5, and the gain is 2. We need to bend a piece of pipe with a stub of 12 inches and a leg of 20. Total pipe length required would be: total pipe length equals 12 inches plus 20 inches, stub plus leg, minus 2 inches, gain. 12 inches plus 20 equals 32 inches, 32 inches 2 inches equals 30. Total pipe length equals 30, as shown in Figure 13-17. To lay out the pipe for a 12 inches stub length, we would subtract 5 inches for take-up and place a bend mark on the conduit 7 inches from the end of the pipe as shown in Figure 13-17. Bend the 90 degrees stub as shown in Figure 13-18. Locating bend mark from opposite end of the pipe. To tind the distance from bend mark A to the end of the leg, Y, as shown in figure 13 to 18, we add 5 inches take up plus 20 inches for the leg length and then subtract 2 inches for gain, making the distance 23. Another way to get the measurement from bend mark A to the end of the pipe, point Y, is as follows. If bend mark A is 7 inches from end X and the pipe is 30 inches long, then bend mark A must be 30 inches 7 inches equals 23. Figure 13 to 19 shows two right angle bends. Mark A is 5 inches before the first angle and mark B is 5 inches before the second angle. The distance from mark A to mark B then is 5 inches plus 47, or 52. In figure 13 to 20 the bends are not at right angles, but are bent on a radius. The distance from bend mark A to bend mark B would be 5 inches plus 47 equals 52, minus 2 inches for one gain for a distance of 50. For double 90 degrees bends, the back-to-back distance minus one gain will be the spacing, or distance, between bend marks A and B. The back-to-back measurement is 52 inches, 52 inches 2 inches equals 50. Now that we understand how to use take up and gain, we can locate other bend marks on the pipe from a preceding bend mark. Example. In this example we will be using 1/2 rigid conduit. Our bender has a take up of 5 inches and we have bent scrap pipe and know the gain for each 90 degrees bend will be 2. Using this information, let's lay out bend marks A and B for the pipe job as indicated in figure 13 to 21. To find total pipe length required, add 12 inches plus 52 plus 24 equals 88. From this total we must now subtract 2 gains, one for each 90 degrees bend, for a total of 4. 88 inches 4 inches equals 84, will be the total pipe length required for this job. The distance from the end of the conduit to bend mark A will be 12 inches, stub length, minus 5 inches, take, up, or 7 inches as shown in figure 13 to 22. Table 13 to 23 offset constants for Chicago-style benders. The back-to-back measurement between the two 90 degrees bends in figure 13-21 is 52. The spacing between bend mark A and B then is found by subtracting one gain of 2 inches from the back-to-back measurement of 52. 52 inches 2 inches equals 50. Distance from bend mark A to bend mark B as shown in figure 13 to 22. This same technique could be used for 3 or 4 90 degrees bends if required. The next example will have an offset and will use pre-positioning offset method number 1 for bend mark layout. Method number 1 is the only method that will work for push-through bending. Note: for bending conduit on a Chicago-style bender, the offset constants shown in table 13 to 23 are used. Using the same bender from the previous example that had a take-up of 5 inches and a gain of 2 inches when bending 1/2 rigid pipe, lay out the pipe as required in figure 13 to 24. The offset will be bent at 45 degrees. Total length, 18 inches plus 37, plus 22 inches, total dimensions, plus 3 inches, shrink for 8 inches offset, 4 inches, for gain for two 90 degrees bends, equals 76, total pipe length required is 76. To locate bend mark A from the end of the pipe, subtract 5 inches, take up, from the 18 inches stub length, that give us a measurement from the end of the pipe to bend mark A of 13, as shown in figure 13 to 25. The distance from bend mark A to bend mark B, using method number 1 for pre-positioning offsets is found as follows. From bend mark A to the back of the bend is 5 inches, take up. From the back of the pipe to the edge of the obstruction is 20 inches, as shown in figure 13 to 26. If it were not for the gain of the 90 degrees bend, we could simply add 5 inches plus 20 inches for a total of 25 inches to find the distance from bend mark A to the edge of the obstruction.